is session type concurrent programming. Is that right? Okay, that's good. So I'm going to call it session type concurrency. And actually in this first lecture, after some previous experience of lecturing here and elsewhere, I'm just going to focus on something very basic, which is the sequent calculus. And I'll spend a little bit of time explaining to you why I'm doing it this way. So today there's actually not going to be, at least this morning, there's not going to be any programming. Or rather, the programming is obscured so you don't actually see it, okay? Even though we're really going to do it. So I'm going to start with a little quiz, okay? So let me do it over here because it's really an aside. All right, so on the left-hand side, I'm going to do it imperatively, okay? I'm going to do the following thing. I'm going to say sort of A, and then I say x equals A at 0. Over here, I'm going to do it functionally. I do something like head composed with sort, okay? So I don't know which camp you belong to, and maybe you do both, like I do both. But you can probably figure out what these little code fragments are supposed to do. So for example, let's take this one here. What is this supposed to do? Yeah?
Find the minimum of A.
Find the minimum of A. So presumably A is some kind of array because we access that with this notation, which should be arrays, right? Presumably sort will sort this array somehow, maybe the minimum element coming first, and then we return the first element and store that in X. So X should be the minimum, or if we sort in reverse order, maybe the maximum element of the elements in the array. And this composition, you have two functions. What does that do? Does the same thing, right? It's a function composition, so you have to read it from right to left. We get sort presumably takes some list, it sorts it, and this takes the head of the list. So we get also maybe the smallest element of the list, right? Okay. So why am I showing you this example? I'm showing you this example because whenever we program, whenever anybody programs, whether they study logic or programming languages or not, okay, they have to reason both operationally and logically. And what I mean by operational reasoning, I think is pretty obvious. We have to reason about how the code executes. So we say, okay, well, first this statement is executed, then this one, okay? Presumably this sorts the array A in place, so that's what it does. And then we execute this one next. We access the element at index 0 and assign that to X, okay? So that's the operational reasoning. But there's also logical reasoning going on here because you are not actually supposed to care about how the sorting function is implemented. It could be a heap sort or a merge sort or a quick sort or whatever, right? And I don't actually have to tell you. Even without me telling you how this function is implemented, you still knew what it was going to do. And that's because when you reason about it logically. You reason about what it actually accomplishes. Just like here, what does this function do when it takes its argument and gives its result to here? It takes in a list and gives you back a list in sorted order. But how it does that, it doesn't matter, okay? So the logical reasoning is about what does the computation actually accomplish, and the operational reasoning is how does it do it? And it's inevitable whenever you program, whenever you do any computer science, you're doing both operational and logical reasoning, okay? Everybody believe that? And that's even if you don't have any formal system of for logic or intuitionistic logic, whatever in mind, it doesn't matter. You're going to be forced into it, okay? So, what we study in programming languages is the following, at least this is my personal point of view, okay? So, all right. Starting to already get kind of weak here, okay? So we design abstractions programming abstractions to capture computation, certain forms of computation. And by programming abstractions, I mean, just for example, a function is a very common programming abstraction, okay? Or interaction is a programming abstraction. Changing memory, accessing memory and changing it, updating it is an abstraction. So we designed the abstraction to capture some computational mechanism, or maybe I should say computational mechanism or phenomenon, such that, okay, that we can reason about it operationally, and we can reason about it logically, and the two things actually fit together, okay? Because we have to do both, because we have to reason logically and operationally. So we can A, reason operationally. We can B, reason logically. And these two things are coherent. Okay, so you have a good programming abstraction if whatever abstraction you have lets you reason about how it executes, what it accomplishes, and these two things actually fit together. Okay, so that's the study of programming languages for me. And then the other things that come on top of that is, well, then we actually try to prove that these properties are okay, not just state them, not just assert them, but our methodology actually requires us to actually prove that when you reason logically, yes, that actually makes sense with respect to the operation of reasoning. And then you also relate them. For example, in a compiler, you might relate a high-level abstraction to a low-level one. Then we want to prove that, yeah, you can translate from here to here and things are still okay. So first we reason about the abstraction by themselves, and then we relate them to each other. And every time we do that, we actually want to prove that this reasoning that we do actually really does work. Okay. So this pervades all of programming language research, and therefore I think it's very important because people are generally, students and practitioners are generally very familiar with operational reasoning, but they're not very formally or seriously introduced to logical reasoning. And so that's why I'm spending this first lecture talking mostly about logical reasoning, namely the sequent calculus. Now, moreover, there's many connections, because if you find good abstraction, there are many connections between operational and logical reasoning. And one of the consequences of that is that a lot of the notation techniques and mechanisms that we actually use to communicate in programming language research were actually borrowed or co-opted from logic, okay? And particularly if you look at any paper in like one of our flagship conferences, you see inference rules, okay? These inference rules are, of course, come from logic, right? They're from the second half of the 19th century, okay? And were further developed into the 20th century, in the early part of the 20th century, before we even thought about computers, okay? But we use these notations because they're effective at communicating even operational concepts, logical concepts, and also how they're related, okay? And so because of that, I want to very carefully and slowly introduce you to the techniques that we use to describe logical reasoning, because they're being used, in any study of programming language, or many of them, they're being used in the same way, okay? And I tried to boil it down to something very, very simple. And the sequent calculus actually is already too complicated. So I'm actually going to take only a small fragment of the sequent calculus that I'm going to show you today. It's small enough that we can look at the various aspects of it and maybe even prove some theorems together. And my intention is that there's not going to be a lot of things, hopefully none, that, you have to look up, you have to read about later, you have to spend five hours studying tonight to figure out what I'm saying here. Everything that I'm saying on the level of definitions and proof, okay? I want that to be fully understood, not like, oh yeah, there's some vague idea. I want it to be actually very concrete. So it's your responsibility to stop me if it's not, okay? So please take that responsibility seriously, okay? All right. So what is logic actually? Well, if you Google it, you find out it's a wrapper, okay? you actually have to go down way down into the second or the third page to figure out there's something else about logic. Okay. So when I was a graduate student and I had a qualifying exam, the first question I was asked is, what is truth? Okay. So I should have said that, well, I'm sorry, but logic doesn't have to do anything with truth. Okay. But I probably would have failed. When you eventually get to the right article in Wikipedia, you find that logic is the study of the principles and criteria for valid inference and demonstration. So that means it's not really about truth, but what you can deduce or infer from other things. It's about the process of deduction. So it's not about, oh, I'm holding this marker in my hand. Maybe now I'm not holding it in my hand. But what you can deduce from the fact that I'm holding it, or in general, what you can deduce about, from if you know one thing, what can you deduce from that, which may be another proposition, okay? So it's all about inference rather than truth, okay? So we're going to start by introducing the Sequent Calculus. And we're going to start it for something called Singleton Logic. Okay. All right. And of course, the lessons are supposed to apply to other sequent calculi, other logics, and so on. But this is like the simplest essence that I could think of. Okay. So a sequent has this form. Okay. A entails B. Okay. Now I need to explain what these various things are. Okay. So this thing over here, both A and B, these are propositions. So these are the things that could be true or they could be false. That's what these propositions are. The thing on the left-hand side of this turns-out symbol is an assumption. And this could be a conclusion, but we also refer to conclusion as sometimes what's below an inference rule. So I try not to use that term. So to make a more neutral term, we'll call these antecedents. And we call this a succedent. Okay. But generally it is that given knowledge of A, I want to show under which circumstances I can deduce knowledge of B. Okay. So sometimes we call this here entailment. Okay, when does A entail B? So in the early days of logic, of course, entailment was very important. Then Hilbert thought it was a bad thing and tried to get rid of it and just say, well, we don't need anything on the left-hand side. We just think about when something is true and not when something entails something else. But then you're not really studying deduction as such anymore. You're studying something slightly different. So we're just trying to do it like this. Now, I'm tying my hands behind my back because I'm telling you right away that there's only one assumption and one conclusion. Okay, and that's why we call it Singleton Logic. Because generally when you work in mathematics, of course, you have many assumptions that you're working with. So this is much too weak to be able to do anything interesting in mathematics. Just try to think about proving Fermat's last theorem only using a single assumption. Okay, it's not going to be really possible. But as it's going to turn out in the later lectures, computationally it's not actually trivial. It looks very trivial, but we can make a slight change of perspective and it's actually something very interesting, and it's going to have something to do with concurrent programming, even though this might seem very, very odd to you right now. Okay? All right. Okay, so we have the Singleton logic, one assumption, one conclusion. And so then we ask, what are the laws of deduction that should hold for Singleton logic? Okay? And these laws are expressed as rules of inference. And rules of inference are usually written with these horizontal lines, as we will see. And we're going to start doing that. So the first very obvious thing is that if you know A, you should be able to conclude A. I mean, what else could you do with an assumption, right? That's an obvious thing to do. So we have a rule like this. If we know A, then we can conclude A. And we call this the identity rule. And sometimes we put the subscript A just to remind ourselves what the proposition is that we're proving. Okay? By the way, is this big enough to read in the back? What happens as the lecture goes on, I write smaller and smaller. Please stop me if that happens. Okay? Okay, so the identity rule should be uncontroversial, right? Okay, now the second one is going to be a little more interesting. Okay? The second rule is that if A entails B and B entails C, then, okay, so always read these lines as if then. So this line says if nothing, without anything, I can conclude A entails A for any proposition A. And this was if A entails B and B entails C, then, and I'm going to write something down here, and you can probably, you either know or you can guess what that is. A entails C, right? So in Singleton Logic, that's the transitivity of entailment. In general, this is called cut. And sometimes we put the formula we're cutting out at the bottom to remind ourselves what that proposition is. Okay? And again, these two rules basically fix this idea that this is an assumption and this is a conclusion that we derive from that assumption. If we have assumption A, we're allowed to conclude A. If you conclude B from A, then we're allowed to assume it in order to prove C. Okay, then that's good enough to show that A entails C. Okay, so in mathematics, in the general case, this is sometimes a lemma. Okay, so to prove C from A, you introduce a lemma B, you show that from your assumption, and then you use a lemma to prove C. Okay, so the weird twist is here that when you do that, you forget A, right? Whatever you know about A is going to be somehow present in B, and then you only have B left to prove C. So again, like I said, if you want to do mathematics, you're going to be very severely limited. But if you want to do programming, it's still interesting. Okay? Okay. Everything okay so far? No controversies? Whatever? Okay. All right. Okay, so I haven't actually told you any concrete propositions because these laws hold for any propositions A, B, and C. So these inference rules are always schematic. And I don't write any quantifiers on these. I just, if I have a free variable A floating around here, I mean, you can instantiate with any concrete proposition A and it should be true. And it shouldn't matter what the proposition is, right? Okay. So now we have to introduce some logical connectors to build bigger propositions from smaller ones. And I'm going to start with disjunction. Okay? So disjunction, so somewhere here we're going to build up our propositions. So propositions A. Okay, so the first one we're going to use, well, actually B and A plus B, and there's going to be more to come. Okay, so I'm going to write A plus B instead of A, this little wedge for OR, because it turns out that it has a slightly different properties from the usual OR. And therefore, it's good to distinguish it. Okay, so plus stands for OR. Okay, so now how do we actually define propositions? Okay, so there's a so-called verificationist school of thought, which says that you define a proposition by saying when you're allowed to conclude it. Okay, and then there is a pragmatist tradition that says you define a proposition by how you're allowed to use it, okay? And hopefully, if we do our job right, those two point of views will actually coincide. It shouldn't matter whether you're a pragmatist or a verificationist, you should come to the same conclusion. And we'll see it towards the end of this lecture what that actually means. But if I want to demonstrate to you what disjunction is, I'm going to define as a verificationist when you're allowed to conclude it, okay? I'm going to do it like this. So A proves B or C if A proves B, and I call this plus right one, okay? So it's a rule for plus. It works on the right-hand side of the tristle with the succedent. That's what the R means. And the one just means it's one of two because you can guess what the second one is, right? The second one should say, well, if I know A, I can conclude B plus C if A entails C, and this would be the second right rule for plus. Okay, makes sense? Okay, so that's my definition of plus. And then we would like to think about some properties of plus. Let me put some over here. Okay, so for example, we want plus or disjunction to be commutative, right? We want, for example, that A or B proves B or A, because the order of the choices shouldn't matter, right? If you can choose between A or B, that's the same being choosing between B or A. So in order to do that, we need to define what you get out of the assumption A plus B, right? How do you actually use that? And so for that, we have to define the left rule. There's several left rules. And the left rule would be if I know A plus B, I'm trying to prove C. Then I have a left rule. And then I have to put something here. So if we know A or B, how do we proceed in a proof in mathematics if we're trying to prove C? Yeah? We distinguish the two cases, right? If C follows in each case, then we know we're good, right? So we have to show A entails C, and we have to show B entails C, okay? So we're pretty happy with these rules. But of course, we need to show that they actually satisfy at some abstract level some criteria that means that this is a decent logic so far, okay? So for example, if I'm not trained and I haven't taken this course and I don't know how to define logics, okay, maybe I make a mistake. And I say, okay, A plus B proves C if A proves C. Okay, and say, okay, so this is my very questionable plus left rule, okay? But is it questionable? It's wrong, right? It has to be wrong in some case because, you know, it's possible that B is true, but I'm not accounting for that, right? I'm only proving C if it happens to be A. So it's wrong. But what actually goes really wrong with the inference system? Like can you demonstrate to somebody walking in the door and you look at this and you say, look how ridiculous that rule. How do you show them that it is ridiculous, okay? Okay, so I'm going to pause here. Yeah, do you have an idea? You can prove false. Well, we only have what's on the board here. We don't even have false. Yeah, so, okay, so already with what we have on the board, we should be able to see that this is completely wrong. So talk to your neighbor, okay? Think about this for a few minutes. Figure out, how can we demonstrate to somebody walking in the door that this is completely wrong? All right, my favorite stuff. There's surprisingly little on the board, but it's surprisingly tricky to show. Yeah. You don't have any experience with this stuff, right? It's funny, it's wrong, but in which way? So somebody who's figured something out. I'm going to make a proposal. Yeah?
So I think if you suppose A entails B, say.
Okay, I suppose A entails B.
And then from that you deduce by the correct right rule that A entails B plus C.
B plus C.
And then you cut that with B plus C entails C.
Okay, so is that true here? B plus
Well,
C?
we can use the left rule.
We can use this wrong rule.
And that gives you C entails C.
Equals C, and that's the identity, so we can apply cut. Okay? And that says then, what does it say? A entails C. Okay? So what's objectionable here? Yeah?
You had to suppose that A entails B. The proof is still open.
Yeah, so what this basically says, if A entails B, then A also entails C. A, where A, B, and C are arbitrary. Okay, that seems a little off, right? If A entails anything at all, then it can also entail C. But actually, we know something that A entails. What is that? A. So I can actually make this A, make this the identity, make this A, this A. Okay, so now what we have shown is that under no assumption whatsoever, because we have finished all the proofs, A entails C, or arbitrary A and C. So our notion of entailment is now completely trivialized, right? Everything entails everything else. No matter how many things I add to my logic, okay, I can always, come back and say, well, you're really in trouble with this logic because anything entails anything else, right? You really want to identify the valid laws of reasoning and not arbitrary laws of reasoning, okay? So yeah, so this rule would lead to this derivation, okay? And so that means that anything entails anything else, which is as close as we come to a contradiction without actually having falsehood. Okay, excellent. So one of the questions we'll have to ask, how do we prevent something like this happening? Okay. What do we have to check of our logical rules to make sure that we don't make a mistake, okay, that our rules are actually make sense? So let's do a couple more connectives and then let's ask the question again. Actually, with the correct rules, just as a little exercise, let's see how we prove that disjunction is commutative. Okay, so how many rules could possibly be applied here? 4 rules, right? We could apply the plus left rule because there's a plus on the left. We could apply this plus right and this plus right, or we can apply cut. Right? 4 possible rules. Now we're smart, so we know which one to apply. Which one do we apply?
Left rule.
The left rule. Okay, so from A we have to prove B plus A. And from B we have to prove B plus A. And that's the plus left rule. And how do we prove from A B plus A? We use the plus right 2 rule. A proves A, which is the identity. And here we use the plus right 1 rule. B proves B, which is the identity. Okay? Okay, makes sense? So that's how you actually reason. Now, if you actually study logic, you study lots of things about strategy, like how to actually, how can I try to prove that? What kind of strategy can I try to prove it? When do I have to make a choice? When do I have to guess? And when I can just proceed and things like that. So we'll come back to that either at the end of this lecture or the next lecture. Okay, so now I want to define another connective. Any proposals? And the requirement is that I can state the rules for it, or it makes sense in the logic where I have one antecedent and one conclusion. Or one subsequent. So not all connectors make sense of that way. So for example, we all love implications, right? It's a wonderful connective. Okay? So A entails B implies C. Alright? So the problem is we need to, well, the way you prove an implication is you assume B and then you try to prove C. Right? You assume B and try to prove C. Right? And then it would be A comma B proves C. And oops, we have more than one assumption. Okay. So we don't have implication. Okay? Because we can't state the rules for it sticking with our hands behind our backs. So what other connections would we possibly have is one antecedent, one succeedent? Not? Okay. All right, so A proves not C if so the way I'd like to state it, okay, of course I have 35 years of experience. I would say A together with C gives me a contradiction. That's what I would like to say. But that would be A together with C, so two assumptions. Back there.
And
Conjunction, okay? So maybe, okay? So let's try conjunction. We'll start by defining on the right rule. So A proves B with C. Well, both obviously we have to prove B and we have to prove C, and this would be the right rule. I'm going to write conjunction like this instead of a little wedge, again because there could be confounding things with the ordinary notion of conjunction, but okay, so that would be the right rule. Now I have to worry about the left rules, right? So the thing that we cannot do, okay, is the thing you would be tempted to do, which says that if I have A with B to prove C, then I have both A and B to prove C. Right? We cannot possibly do that because we're not allowed to have two assumptions. Okay? So that's bad. Okay? But we can recover. So how can we recover? Yeah?
you can do the same thing as with R right and R, yeah. You
Yeah, we
just
do the same thing as
do
before,
C
right?
or C.
For left, we say A with B through C is A through C. So this is the first left rule. And the second one would be this. Okay. Now, there's a general principle here, which is that because we only have exactly one thing on the left, one thing on the right, there should be something symmetric for everything we can do on the other side, right? There's a very strong symmetry principle that we can apply because we just flip the rules, right? The rule with two premises on the left becomes this with two premises on the right, and two rules on the right become two rules on the left. And then we look, what kind of connected is that? Well, it's a form of conjunction in those things. Okay, and hopefully we didn't screw up. Okay, we don't know that yet, but hopefully we didn't screw up. Okay. Now, now we can ask some questions. Okay, for example, we could ask, do these things like distribute over each other? Okay. So let's try that. Okay. So for example, we might want to ask if A with B plus C. Okay. Entails, I'm going to write it like this, entails in both directions, which we need to distribute because they're equivalent, with some kind of distributivity. Okay, does that statement make sense? And this is something we should investigate? Yes. Makes sense? Okay. So let's see. Now, either we want to have a feeling of success, or we want to have a feeling of failure. If you want to have a feeling of failure, you try the one that you're suspicious of, and maybe you find it doesn't work. Okay. If you want to have a feeling of success, you pick the easy direction. Okay. So when I was working on a PhD, I was working on a theorem in, well, kind of proof theory for a while, and I really liked the feeling of success. Right? And in that particular proof I was trying to do, there were 64 cases. Okay. Guess which 63 I did first. Okay. And then, of course, 64 didn't work. Okay. And there was no way to fix it. And I had to switch topics. Okay. Now here we don't have to do that. Okay. So don't worry. Okay. I'm not going to like abandon the next 4 lectures. Okay. So let's try to have a feeling of, well, let's just see. Okay, let's just put one of these because we're used to thinking these. Okay. All right, how many rules could be applied here? Four. Okay, 2 on the left, 2 on the right, that makes 4, and cut. And cut makes 5. 5, right? Okay, so let's say we're trying to say, well, maybe it's the case that A implies A with B, or A with C. Okay, so that would be, I'll write that in here, the with left 1 rule. Now, you should be suspicious of this statement. Okay? Because now we can't do anything on the left. To work on the right, we could always do cut, but if we don't do cut, we could do this, or we could use that. Now, to prove A with B is going to be impossible because we don't know B. To prove A with C is going to be impossible, we don't know C. So intuitively, we shouldn't be able to prove this because we don't have enough assumptions. Whether in the formal system we can prove it, we don't know, but we think, okay, this is not going to work. All right, now, okay, maybe that was just dumb, and we should try to prove instead that B plus C entails that same thing on the right-hand side. Okay. Now what? So now, yeah, similar problem. Now we can use the or left rule here. We have to prove the right-hand side from B, and we have to prove it from C. But we just have B, or we just have C. But here we have to have A, and here we have to have A, but we don't have A anymore, so it shouldn't work. Somehow intuitively it shouldn't be the case. Okay, so we can't start on the left. Now, can we start on the right? Can we prove A with B from A with B and C? That looks a little more plausible. Okay, so let's try that. All right, so we have A with B or C proves A with B. And if you tried this, it would be symmetric, right? So trying one should be enough. All right, so now we can do the right rule here. Well, that's just enough to show the right rule that A with B plus C proves A, and A with B plus C proves B, right? Those are the things. If you prove a conjunction, you shouldn't break up into two. Okay, so now here, what do we do? Okay, this looks like pretty promising, right? Because we can pick either A or B plus C, right? We have the two left rules, so we just pick A, and we say success. Right? We pick A, and then we use the identity. Everybody with me on this? Okay, so this is good. Now here we're trying to prove B, so we don't want A, so we pick B plus C, and we try to prove B. Okay? Is our rule still out there, or a highly questionable rule? Okay? So if we could pick just the B, it would be okay. But we can't, okay? We just said this is bad, bad, bad. Okay, so actually here we get stuck. Okay. But actually we aren't really stuck, are we? I mean, we can apply the or left rule, and in one case B proves B, in the other case C proves B. Well, C proves B is unlikely to be true for arbitrary B and C. Okay, so, but we always have cut. Maybe we just couldn't find the right lemma. Okay, maybe we're just stupid, and maybe the right way to prove is B plus C proves some magic lemma, and then magic implies B. Right? Okay, so now. All right, so now we try that, okay? Proposals for the lemma. Well, B would be great, because then we would know this. But oops, we haven't really made any progress. So maybe B with C. Well, okay. So you can see that it's very hard with the system that we have to show that something isn't actually true. That you can't prove it. Because at any point in time, no matter what your conclusion is, you can say, well, maybe I just need a lemma, right? This is actually the case of mathematics, right? You're trying to prove, Goldbach's conjecture. You just need the right lemma and you'll be done. Okay? But what is the right lemma, right? That's the question. Okay? But here, with the simple logic, it shouldn't be that hard, right? We only have plus and width, right? We only have on the board all the rules. I was able to show it to you in like 45 minutes, plus figure out some things that are actually wrong. Shouldn't be that hard, okay? Okay, so the question is, by the way, the other direction, I think works. Okay. But I'm not interested in success. Failure is much more. That's what I learned as a grad student is still true. Okay, so we're going to accomplish two things at the same time. Okay. So we're going to try to accomplish the following. We're going to try to give you, I'm trying to give you a tool for showing that something isn't actually true in the logic. Okay? And I'm also going to try to give you a tool to prove that I have the correct set of rules, and the weird thing that happened over there, but I screwed up, okay, is not going to happen. And the tool is called cut elimination. And this theorem, a much more complicated sequent calculus, goes back to Gensen 1935. Okay? And I should have said at the beginning that the sequent calculus in general goes back to Gensen. But what I'm showing here is just a small fragment of it. Right? Small enough to be, turning out to be computationally interesting. Still computationally interesting, but I can actually show these various parameters of it. Okay. So what does cut elimination actually mean? So what we want from the rule of cut is that if I can prove B from A, I'm actually justified in assuming B. Okay. So it's not just that whenever A entails B and B entails C, then A entails C, but I'm actually justified in making that assumption. So I should be justified in making this conclusion without using the rule of cut. That means I can't deduce anything from A that would actually be like, lead me to conclude something that wouldn't follow from A already. Okay. So what we want is that to show that the cut rule is actually unnecessary. Okay. We don't need the cut rule. Well, it may be sometimes helpful. Okay. May lead to shorter proofs maybe or something like that. And it's generally useful in mathematics. Okay. But at this very small logic, you don't actually really need it. If there is a proof, there is a proof without using the rule of cut. Okay. So that's what I want to show. And so the two consequences of that is, let's say I have A and A and C, the thing that where I don't know anything about A and C, they're just variables. I'm not telling you what they are. How many rules apply, but I don't have cut. Yeah? None, right? No rule applies. So I cannot prove this if the theorem of cut elimination is true. So I can't screw up maybe in other ways, but I certainly cannot screw up in this way. Because it's impossible. Okay? And in fact, here is an example where I have a rule of cut to conclude A and C. Okay? But I cannot eliminate it from this proof because I had an incorrect rule like over here. So I cannot actually get rid of this. It's essential. Because I can conclude something from A that I'm not really supposed to be able to use to get that proof. Okay. So I cannot prove this unless I know something about A and C. So an easy consequence of cut elimination is that your logic is consistent in the sense that you cannot prove everything. Now, usually it's formulated to say we cannot prove a contradiction, but since we don't have falsehood here, I'm just saying that we cannot prove everything. That's a very weak statement about the logic, but it's actually still useful to know, right? And the other thing is that if I know that I don't have a cut rule, okay, then if I look at my rules here, each of the rules, if you read them from the bottom to the top, because you have a conjecture at the bottom, you're trying to use the rules, okay? They eliminate the connected, okay? So with plus, plus, plus. So all the premise is always smaller than the conclusion, right? Because you get rid of these things. So if you're trying to prove something, there may be some choices about which rule you apply. But in each case, eventually, you will either say, okay, I'm going to use the identity, or you will fail to be able to prove it because no rule applies. Okay, does that make sense? Okay, so for proof cut elimination, we'll also know that our logic, this very simple logic, is decidable. Because the premises of each rule are always smaller than the conclusion. So I can just stupidly try them all, or I can smartly try them all, but it doesn't matter. There's only finitely many things I can do because all the rules break down the connectors. Okay, everybody believe that? Okay, we wouldn't have to guess whether we can prove that. We can actually try all the possibilities, and if they're all failing, okay, this is not a theorem of Okay, so cut elimination is a very simple theorem. And it also has very important consequences of computations that we'll talk about in another lecture, probably the next one. Okay. Oh, by the way, propositions down here, we have also with you. Okay. So now we have to ask about how do we actually prove cut elimination. Okay. So let's try to think of a simple example how cut elimination actually works. And let's see if we can abstract something from that. Okay. By the way, normally in a lecture it would be totally hopeless to try to prove this. But actually, this is a very simple logic. Maybe we can actually do it. Okay. So I want to have something where I use cut in my proof, but not completely trivial. So I'm going to do it like this. I say A entails A plus B. Okay, that should be. Okay, how do we prove it? Well, A proves A because this is the plus right 1, and this is the right. All right, now then I know that A plus B is symmetric. And how do I prove that? Well, I use the plus left to prove A proves B plus A, and also B proves B plus A. And here you use the plus right 1, B proves B, which is identity. And here I use plus right 2, A proves A, which is identity. And then I use cut to show that A proves B plus A. Okay, so cut might be useful. It wasn't very useful here. Right? Because there's a much shorter proof of this thing, right? So if we're lucky and we do play our cards right, then maybe cut elimination is something like if we replace this whole proof by the proof that uses the plus right 2 rule, and then uses the identity, maybe. Okay. Maybe some other weird proof, I don't know. Okay. We'll have to figure out what that is. Okay. In fact, no, I'll take that back. It'll have to be that proof. Because there's only one proof of this thing. You don't have the rule of cut. Right? Normal applies on the left. If you try to use B while A doesn't entail B, you're stuck. You have to use the other rule, A proves A. And that's the identity. So there's only one way to prove this without cut, which is essentially like this and using the plus right 2 rule. So when we apply cut elimination, we should take this very complicated proof and we should end up with this very simple proof. That's not always the case, but in our logic, actually, I think it is. I'm on camera. Okay, I conjectured it. All right. So, if you look at this particular proof, how do you think we could sort of stepwise see or eliminate this cut? Any ideas? Okay, so here's an idea. The plus left rule accounts for the two possibilities that either A might be true or B might be true. That's why we have the two premises, because we don't know when we have A plus B if it's going to be B. This proof here on the left actually tells us which one of these two. Which one? A. So this whole thing you should drop out somehow. It's irrelevant, right? Because we know actually from this proof it's actually A that is true rather than B. Okay. So somehow this part of the proof should be irrelevant. We should be focusing on this. But what does it mean to focus on that? So what we do is something we call pushing up the cut. Okay? We're trying to reduce the cut on a complex formula, A plus B, to a cut on a simpler formula. And the simpler formula in this case, we look at the structure of the proof, we see what it is. So here it's A that was chosen. Okay? And that means we need this branch over here, not this. Reduce this whole thing. So this is some kind of proof reduction. To take this proof, A proves A by the identity. And cut this with this part of the proof. A proves B plus A. Because we have plus right 2, which follows from A proves A, which is the identity. And the conclusion is still A proves B plus A. Okay, does that step make sense? You want to stepwise get from our initial proof to the one that doesn't have any cuts. And so the way we do that is we push out the cut. We look over here, we see, oh, it was A. And so we only need this branch here, because this accounts for both cases, but the case B we don't need. And we create a new cut here between that two. Okay, so now how do we proceed now? Now we see that this formula here is the one that we're cutting out, which is the same as this one, which ends up out here. So these formulas are the same, because this is the identity. If this wasn't the identity, this formula would be different from this. But because this is the identity, these two are the same. So cut and identity cancel each other out. And we just end up in one more step. Okay. Where this proof A is B plus A, because plus R2, A proves A, which is the identity. Okay, so it requires two steps, but we were able to get there. Okay. So we need to take this intuition that we have here and pass this into a formal proof about our deductive system. Okay. So the way we do that, okay, there's many ways to do this, because it's very important here, many proofs have been published. But one thing that we often do in programming study programming languages is that if you want a particular property, we express it in the form of a set of inference rules, a new one. Okay? So rather than saying, oh, it's a proof and it doesn't use cut, we define a whole new judgment. Okay? And then we have two things that we can explicitly relate to each other. Okay? And the new judgment, I'm just going to use a very different symbol so it's kind of obvious. A and K is B. Okay? And for this one, I'm going to replicate all the rules, but I'm going to omit cut. Okay? So in particular, I have a rule like A plus B without cut through C is A without cut through C and B without cut through C. And I have two rules that say A without cut through B with C, B plus C, A without cut through B, or B plus C is A through C. Okay, and actually, let me give them the same name. Plus left without cut, plus left 1 without cut, and plus left 2 without cut. Okay? Okay, so this is not necessary to do it this way, but it turns out to be often a very good way of organizing proofs. And then there's more rules, right? All the other rules are replicated except the rule of cut. That's a critical part. Okay, so that means A and S P without the rule of cut. Okay, everybody with me on this? Pretty straightforward, right? So now our theorem that we want to prove, determination is that if A proves B, then A proves B without cut. Does that make sense as a theorem? All right, that's what we want to prove. Now we can state it very clearly. Yep. Oh, yeah, sorry. Okay, so let's try to prove that and let's see what happens, right? So when you have a conjecture like this one, it's often very helpful to actually try to prove it and see what goes wrong. Or if nothing goes wrong, then you're happy, but since I'm always interested in failure, probably not going to happen. Okay, so the important principle that we use here in this proof is induction over a structure over a deduction, or sometimes called rule induction. So the proof of this theorem, proof by rule induction And the study of logic and the study of programming languages is full of these things. Okay? You have to do, rule induction all the time. And this is because we express everything by rules. Okay? So then what do you have? Well, rule induction. Okay? Well, what does rule induction actually say? So I'm given a proof of A equals B by using these rules up there. Okay? And I want to establish a property for every possible proof of this. There exists a proof over here. Right? So I need to prove something for all deductions of A equals B. Let me call these deductions, and these are proof of the meta theory. For every deduction of A equals B with these rules, there should be a deduction of A equals B with these rules now. That's what I've found. So how do you prove something for every possible deduction? Okay. So when you look at these rules, and you say, these are all the rules I have. There's no more to come. These are all the rules I have. You get out of that, if I want to prove a property of all possible proofs, you can do an induction or the structure of these things. Okay. So what is your base case here for this induction? ID, because it's the only rule that doesn't have any premises, so I have to prove my property outright for that one. Okay. In all other cases, I get to assume my induction hypothesis for all the premises, okay, and I have to prove it for the conclusion. Okay. Now, if I do that, if I can do that for all these rules, then I have established a property for all possible deductions. Okay. Because I'm saying these are all the rules you have, stop here, no more rules to come. You want to subproof on anything that you can deduce by using these rules, as long as you can show that it's always propagated from the premise to the conclusion, it has to hold for every possible proof you can construct. So it's a little bit odd to do this because usually we think of, when you construct a proof, you go bottom up. Right? You prove this, you prove that, well, and then you finish it with the top. But when we do induction, we have to think about it the other way. We have to say, whatever property you want, if it's true for all of the premises, you have to show that it holds for the conclusion. If that's the case, it'll hold for all possible deductions. Does that make sense? Okay, so you really need to understand this because you won't be able to do any work in programming languages whatsoever, okay, unless you know how to do rule induction. But it is actually a very simple principle. Okay. It just says that whatever property you want, you're allowed to assume it for all the premises, so you have to show that it holds for the conclusion. Okay, so let's do that. Okay, let's do it over here. So we have to look at all the possible cases. Now, for once, I'm going to be interested in success. Okay. So let's try to do it for the plus left rule. Okay. So the case is that A plus B is C because A is C. And B is C. Okay. So I have to show that my deduction looks like this. Okay. And I have to put together, I have to show that A plus B can be proved without cut. And then it is C. That's what I have to show. Okay, make sense? That's what I know in this case. That's what I have to show. Now, the first thing you usually do in this proof, you try to apply the induction hypothesis. Right? After you write down what you have to prove, you apply the induction hypothesis. I can apply the induction hypothesis to this and to this, right? That's what it means to do rule induction. You apply it to the premises. Okay, what does the induction hypothesis of this give me? Yeah? Yeah, A and T C without a cut. See, I very cleverly write this in that spot. Okay. What is the induction hypothesis? So this is my induction hypothesis. What does applying the induction hypothesis on this gives me? B entails C without cut. That's my induction hypothesis. I don't know what the proof is, but I know it exists, my induction hypothesis. How can I prove this now? This rule, right? Because I copied all the rules, so you just reapply. So this was plus left, and here I use plus left without cut. And that allows you to prove the cut. Okay. Everybody with me on this? Can you do all the rest of the proofs in a row? Okay, not quite. What about if this was plus right 1? Can you do that correct piece of the proof? Yes, because we apply the Deduction hypothesis, we will apply the rule, we're at the same place. Okay? Because we copied all the rules, except it can't cut. Okay. Right, so case number 64. Okay. Okay, so we have A, there's B, B, and C, and we have cut, we have A and C. So the induction hypothesis here gives us A proves B without cut, B proves C without cut. So that's my induction hypothesis, that's my induction hypothesis. And now we need to say, okay, then A and C without cut. Okay. Ouch. Okay. Have we made progress? Yes, in some way. Because we're now stuck in something. If you're stuck in something, leave the thing in lemma. Okay. That's the advice. Okay. So if we can finish this here by lemma 5, well, actually maybe it's lemma 1 for us, okay, then we're done with this proof. Okay. So the next thing is we have taken the property for a complicated system where cut can be applied anywhere to a simpler system. If you have a cut-free proof of A implies B and a cut-free proof of B implies C, then we get a cut-free proof of A implies C. Okay. So we have reduced our problem. Okay. So, but this kind of thing happens often. So even though these are, of course, examples, I want this up for a while. Okay. By the way, isn't it shocking that this has to do anything with programming? And concurrency? Right? Okay. Okay, next lecture. Okay, so we go forward. Okay. Okay, but now what do we do? Okay, so we have a lemma. And that's called admissibility of cut. Admissibility of cut. Okay, so if A entails B without cut, and B entails C without cut, then A entails C without cut. Okay. So how do we prove that out? Okay. Okay. So presumably it's some kind of induction again. And presumably, since we're in this lecture and I've touted rule induction all the time, it's going to be some form of rule induction. Okay. But we don't know exactly how to apply it. So proof by some induction. Okay. We don't actually know. So when you don't really know, what you do is you look at the cases, just like we looked at that example, and you try to see if you can discover the structure. Well, we're trying to prove a for all exists statement here. For every deduction here and deduction there, there exists one here. So let's try to do this what we call constructively, which means you assume you're given one here, and you're given one here, okay, and try to construct this thing over here. And if you do this the right way, then after you're done with your construction, you can sometimes see why it actually constitutes a proof. Okay? So hopefully we can do that in 20 minutes. I don't know. We can try. Okay. So get rid of this stuff. Because we already know how to prove that. Okay, so now we need to look at different cases. So let's do some easy cases first. And then I'm doing the easy cases first, not because that's what you should always do, but because it gets your feet wet. Kind of like, okay, I can see how they go. So do those easy cases, and then come back to part one. Easy cases, the first one is the identity. So A proves A by the identity. And the right-hand side is just A proves C, and we don't actually care. I'm going to write it like this. we're trying to construct the proof of A proves C. Okay, so if this is A entails B, where the identity is equal to A, so this becomes A entails C. And my conclusion is also A entails C. So how do I construct A entails C? Well, I don't have to do a lot of construction, yeah? I have it here, right? If I'm given that one, so I don't know what to call this. Let's call this E. We just take, okay, and that's a proof of A entails C. So cut and identity cancel each other out exactly. That's like functions, right? If you can throw something with the identity, okay, you get that thing out. Okay. Good. Now if I put the identity over here, the same thing will happen. Okay, so we have already two cases under our belt. Okay. If one of them is the identity, okay, we're good. Okay, so let's tackle a slightly larger case. Okay. Okay, so let's do the one about plus that we used from the example. So I have a plus right rule on the one side matched with the plus left rule on the other. Okay, so the first one looks like, so A through B plus C, and the second one looks B plus C proves D, and this is by A proves B, let's say first right rule, and this one is by the plus left rule, all without cut of course, because B proves B and C proves D. B. Okay. So let's call this here, this proof D, this is called proof E, and this is called F, just so we can refer them. And we want to show that it's okay to cut these two to get out a proof of A proves D. Okay, that's what we want. Okay. So how can we apply the induction hypothesis over here to construct this proof of A plays D, even though we don't even know what induction we're doing? Okay. So how can we construct this proof of A D? Yeah.
The induction hypothesis on D and E.
Okay, we apply the induction hypothesis on D and E. Presumably, they're smaller proofs, so maybe it's okay. Okay, so we have on D, A proves B without cut, and E is B proves D without cut. So then, by induction hypothesis, we should be able to get A proves D without cut. Oh, magic. Okay, that's what we wanted. Okay, so it works. And that's actually exactly what we did over there, right? So the point here is that we're allowed to peek into this proof and see which of these two alternatives actually is true. Because this proof tells us, oh, it was B, so we picked this proof. If this had been the plus right 2 rule, which one would you have picked? This one. Because that would have been a proof of C, and here we have C as an assumption. So we can proceed in both cases. So it works out like that. Okay. And then, are we done? No, we have to consider all the cases. Well, we can't actually consider all the cases, but there's one, okay, so there's two types of cases we've seen so far. One type of case is that one side you see identity, then we're done immediately because cut cancels, identity cancels with cut. And then there's a possibility that we have a right rule for connected matched up with a left rule for the same connected. Okay. And then we can apply the induction hypothesis given the premises to eliminate that. Okay. Now there's one more possible case. Can anybody see what kind of cases we have to be concerned about? Yeah?
Or if it's like a left rule and a left rule.
Yeah, so what is the left rule and the left rule? Okay. So we understand this proof now. Okay, so let's say that applying a left rule here, let's say A with B proves C, and C proves D. I can't write my letters. And the cut is supposed to conclude that A with B proves D. And this here, what's the first left rule? A proves C for width, without cut. And I'm going to call this D, I'm going to call this E. Okay, so actually I don't care whether this is a left rule or not, just to make it simple. But this might have been a left rule, so it doesn't work on this proposition in the middle. Right? So it works somewhere else. Okay. So what do we do in that case? Think about situations like that. Yeah?
You get a new proof where you first apply the left rule, the
Like the
width
left
L.
rule, this one here.
Yeah.
Okay, so we do width left 1, trying to get A proves D. Okay?
Then you apply the induction hypothesis with D and E.
So now we take D and E,
Yeah.
and we apply the induction hypothesis. So A triangle C, and C triangle D, and this is E, and this is E. Okay? So we take this proof over here, and we apply the induction hypothesis, or cut it with this one over here. And so it gives us that. A proves C because we cut D out of the middle. And then we just have to take this rule that was here and apply it again down here to get the right conclusion. Okay. So these are the 3 solved cases, and they all work like that. Okay? So we have to worry a little bit about here whether that's really good induction. But we can look and we can see that this is actually what we described as really an algorithm. We're taking a cut-free proof of the first premise, the first assumption, maybe a cut-free proof of the second one, and constructing a cut-free proof of A and right? So if you're confronted with this situation where this is a left rule, okay, what you do is you look in the premise, you apply your algorithm to these 2 proofs, and then you reapply that same rule. So sometimes you say we're pushing up the cut past this rule. Okay, so this cut here is being pushed up to being applied here. And that means that rule here floats down to be applied later. So we push up the cut. Okay. And by pushing up the cut, we can finally get to a situation that looks like this. We have a right rule match up with a left rule. Okay. And then we push it up and the cut becomes a cut between smaller quantities, this one and this one in this case. Okay. And if you ever hit an identity, the cut just disappears because identity and cut cancel. Okay. All right. So why is this a good induction? Well, in this case, the cut actually disappears. Okay, nobody will argue with that. In this case, we apply the induction hypothesis here to 2 smaller proofs, D and E. Okay. So D was the subproof here, and E was the subproof here. So that's good. Okay, so the tricky case might be here because D is the subproof of this, but E stays the same. Okay, so we have a pair of 2 proofs. Okay, either they both get smaller, or one gets smaller, the other one stays the same. And maybe this one gets smaller again, this one stays the same, but then this one gets smaller, and then this one gets smaller, and so on. Right? That's a perfectly valid induction. We call it something as a simultaneous induction of these 2 assumptions. One gets smaller, the other one might stay the same, one might also get smaller. But eventually we get down to being able to eliminate it completely. Okay? So this is a very special circumstance. Usually this doesn't happen. Usually we actually need a more complicated induction. And what we observe is that in a rule like this, the cut formula here, the cut proposition B plus C gets smaller and it becomes B. We don't need that here, but in general we need that. And then we need to know that in these cases the proofs get smaller. So there the proposition gets smaller and here the proofs get smaller. But here the proofs, all the proofs always get smaller. So it's actually a simpler proof than what usually happens in C kind of. Okay, so this is not yet the full story, but we have now proven here the admissibility of cut, and that's a critical lemma that you need for cut elimination. And this is a very common pattern. You take the property that you want, you build a new system that expresses the property, you prove an internal property of this new system, and that's really all you need. And with that, we know that, for example, the cut rule is not really necessary, and that the thing we're trying to show over there, which didn't hold, like the distributivity law, really is not valid. Okay. Doesn't hold in general for arbitrary B. And we know that this weird counterexample that we had, when we have a wrong left roll, okay, it doesn't actually matter. More importantly, if you think about the semantics, our job was to say we express the meaning of the connectives by the right rules, because we define as verificationists when you're allowed to conclude A plus B, or when you're allowed to conclude B with C. Okay, so I'm defining it by the right rule. Now, if you have a cut rule, that's actually problematic, because the meaning of B plus C, for example here, might depend on some arbitrary lemma which are cut in the middle, which might have arbitrary complex proposition in it. And that really wouldn't really work, because that basically means that the meaning of all my connectives are entangled with each other. But I really only want to talk about conjunction, okay? But if you don't have the cut rule, then you can see that the meaning of this sequel, or the proof of the sequel, will only consist of subformulas. So in other words, our definition of this connective by the rules is compositional. Okay? It doesn't look outside this proposition where it's not proven. So we don't have to worry about that. We might have to come up with some weird lemma that uses other connectives that we don't actually know about in order to understand what conjunction means. So we can independently introduce conjunction and disjunction, and then some more connectives later on, and understand their meaning independently because cut elimination holds as a property. So we call these proofs that don't use a cut form, we call these analytic, because the cut-free proofs that you can construct of these only consist of the subformula which you're trying to prove. You don't have to go outside to try to prove it, you can stay inside that proposition. In mathematics, we're usually not that lucky, okay? But here, for this simple logic and many other situations that we care about, we're lucky enough that we can do that. Okay, so what I'll explain to you in the next lecture will be, what does it have to do with concurrency and computation? So I'll see you this afternoon.
The inability to prove distributivity is the claim that if we know that we cannot, like, I guess the belief that if we know we can't prove it without cuts, then like we can sort of say, oh, we can demonstrate that there's no possible proof of the statement exhaustively, or like what?
That's exactly it. So I'm trying to show that for the distributivity law, the left-hand side does not entail the right-hand side. And so really what I'm trying to show is while it does entail. Okay. Now with this judgment, I have very little hope of proving that directly because of the cut rule. So I say, but I already know if there's a proof of that, there's also a cut-free proof of that. Okay. So now we look at only the cut-free proofs. Now you look at all the rules without the rule of cuts, and you see that each time the premises are smaller than the concluding because you eliminate one of the connectors. And so you might have to try various possibilities if like a right rule and a left rule are applicable at the same time. We don't know, there's non-determinism. Right? But if you try all possibilities eventually have to succeed or they have to fail. There's no other possibility. And that basically shows that we can decide any proposition in this very simple logic simply by trying all possibilities. And it's only because we know that we don't actually really need to cut the rule. There's various refinements of that with strategies to make it even less non-deterministic, but this is the simple story. Yeah?
Yeah, so I would know if the distribution rules in our system, i.e. A with B plus C is conform to A with B plus A with C.
Oh, excellent question. Homework. Now you know how to either prove it or refute it, right?
Yeah.
That's a very good homework. So try the distributivity law in the other direction, okay, with over plus instead of plus over with, and see if that works or not. Two directions to check each direction and see if you can either find a proof or if you fail to find it. very good exercise. Yeah.
You mentioned that in this logic, the size of the cut in proofs was always smaller, or you conjectured it rather.
Yeah.
In other logics, that isn't always the case. Can the cut speed proofs become very large?
Yes.
Okay.
Yeah. So depending on what your logic is, there's always a bound. But in some cases, the bound is so that we don't know any other way to express it except saying, well, it's much, much bigger, and my inference system gives you the bound. These are called so-called proof theoretic ordinals. So it really depends on your logic. It can be gigantic. So here, you have to analyze the proof in the detail, but you see that essentially either the size stays the same or it gets smaller. So after cut elimination, you get a smaller proof. Yeah, so it really depends on exactly the connectors you have to see how much the proof might go up. Other questions?
So is this system complete?
Okay. So I can't answer that question because I haven't proven the right theorem of the system. Okay. So the fact that you can eliminate the cut rule is an internal expression of the soundness theorem before. It's sound. Okay. Now there's also an internal expression of the completeness system of the system. So for example, let's say I make a mistake and I forgot the left rule altogether. You would expect the system to be incomplete, right? Because I omitted something rather essential. Okay. And for example, you would no longer be able to prove that A plus B proves B plus A. Right? If you omit the left rule altogether, you can't really use this assumption to prove that. So the system becomes incomplete. But again, just like with the other thing, what actually goes wrong? Yeah, you no longer prove that. You should somehow be able to prove it, but you can't. Okay, homework. Anything that I don't know, actually, I do know the answer. And maybe I'll actually show it to you later, maybe at the beginning of the next lecture. But meanwhile, think about it. If I've forgotten that left rule, the system should be in some essential way be incomplete. But what does that actually mean? Like, how can I demonstrate to somebody there's something really wrong? Because cut elimination still holds, right? Because I just removed one of these rules. Okay, so it shouldn't suddenly fail when it worked before. Because that just gives you fewer ways to prove things. Okay. Yeah.
Oh, last one, I promise. Do consistent logics always have cut admissibility theorems?
No. Okay. No. Any good logic has cut admissibility. The other things are all bad. Very technical statement. Actually, I'm sorry, I'm on camera. The other logics bear further investigation to see if you can come up with a formulation in which you can demonstrate that the meaning of the connectors is composition.
So if I eliminate cut by putting more axioms, like other axioms that doesn't go to cut,
Yes.
so is that also cut elimination?
Well, I don't want to talk about axioms because, so Hilbert's idea was the following. We should express everything by axioms and only have as few inference rules as possible. So for propositional logic, you have just one modus ponens. For first order logic, you have like two, you have a generalization modus ponens. For modal logic, it has three because of necessitation. Everything else is packed into axioms. If you do that, then it's much harder to dig out some kind of property that's similar to cut elimination. So what Gensen actually did in 35 was he looked at a calculus of natural reduction that was supposed to represent how humans actually did proof, which he thought Hilbert's calculus didn't. Okay? But it should be somehow equivalent to Hilbert's calculus. That's something we need to prove. But then he said, well, on this system of natural reduction, it's very difficult to see if it's consistent. So I'm going to reformulate it as a sequent calculus, and I prove the natural reduction and the sequent calculus prove the same things. And then I show cut elimination with the sequent calculus, and thereby I know that my system is consistent. Okay? And then later on, Proberts came along and showed that you don't need to do that detour. But it was very hard to think in 1935 how to do this directly on other forms of inference to see the same properties. So the Sequent Calculus exposes these properties by the presence or absence of a rule. For other calculi, it's a much more complicated property. You can't just say, this proof is cut-free the way we can say here. It's more difficult to see if you obey the subparameter property and so on. And the other reason I did the Sequent Calculus is because it's easy to prove, and it gives you concurrency. But these are all excellent questions. Anything else? All right. So thanks again.